Hello, everyone. Yeah, welcome to my talk. So this talk is going to be about AI coding agents and how they work underneath the hood. I'm going to talk about one of the more popular coding agents, one that I built with a team of 3 engineers very early on. And we're going to reverse engineer it. We're going to talk about how all the prompts work, the agent coding architecture, and things like that. It'll be really interesting. And also, if you guys don't know who I am, my name is Kevin. I'm one of the co-founders of Firebender. And yeah, let's get right into it. It'll be fun. So, OK, so a lot of coding agents, when you look at them, you'll see this prompt box. And you can type in anything. So this will look very similar to Cursor or Copilot, that sort of thing. And the idea is that you can just write anything that you want inside the prompt. And in theory, the coding agent should just do it. It should just implement the code that you described. Yeah, it makes sense. That is obviously a very good dream and very nice aspiration. I would say to get ready to take pictures on this next slide. And this will have our full architecture here. Oh, sorry, yeah, the slide after this. OK, so this is how it works, yeah. OK, this is a bad joke, but this is not actually how it works. We do not manually code all the requests. So yeah, no, it's not the end of the presentation. OK. No, but we're going to get serious and actually discuss what this is and why this is important. I think it's really important to give just a basic primer on what Firebender is. And I'll give you a sense for some of the things that it can do really quick. So OK, so we're going to start with this very simple YouTube video. Yeah, everyone can see this. So in this example, what I'm doing here is I'm giving Firebender a Figma URL, and we're typing it in the chat box. It's directly in Android Studio as a plugin. You can see one of the first things that it does is it grabs the Figma, the actual preview screenshot, from Figma directly. And now it's going through the code base and trying to find styles and common themes that are already built into the code base. You can see here it's starting to list out directories. One of the first files it reads is the color.kt file, and then the theme.kt file. And then it'll also go ahead and read some of the typography that's configured. So we'll let that run for a little bit. And here it's going to actually make the edit. I'm going to go ahead and speed this up 2 times. OK, so it's going to make this change and actually build out the screen using all the theming and everything. And over here, it makes an interesting tool call where it will actually call this Figma preview comparison. And I'm going to pause really quick before this continues to run. So what you'll notice is that there's 3 images here. There's an image on the left. That is supposed to be the actual code rendered preview. So what we're doing here is we're hooking into the Android Studio IDE to get the actual rendered preview. The Figma target is the center image. That's the UI that Firebender agent is trying to recreate. And you can kind of see also this really nice diff view of the 2 UIs. So you can very quickly visually see where there are some defects. And obviously on the first try, Firebender is not going to get it absolutely correct. You'll notice here that there's some this tab right here is incorrect. That's different. The sizing of the image is also wrong. That's different. So I'm gonna go ahead and hit play back where we were just at. And we'll watch Firebender actually iterate. So what we're doing here is we're giving all of these images back to the LLM for it to actually say, hey, these are the problems. Like, let me try and actually fix those problems. And on the second iteration here, you can see that it's getting a little closer. To the end here, just so we don't watch this full video. And so you can see the final result here. And you can see that it is able to also get like the image sizing and get closer. So what's going on like overall is that we're essentially giving like these really powerful frontier models all the right hooks directly into Android Studio, where it can just start iterating off of its own work. And so this is like kind of the result that you get after just like 2 or 3 runs. And so it can continue on, but yeah, cool. So yeah, so that should give you a sense of like one small feature of Firebender. Okay. Now, the other thing too to note for Firebender is that at this point we have like thousands of engineers that use the tool every day, and it's really kind of crazy to think about some of the aggregate metrics like through the tool. These are essentially the top 10 vibe coders in the world that use Firebender. And I actually have no idea how this is possible, but there are 2 people that have made over 10 million lines of code changed just by using the agent. So this is them hitting accept on the agent and using the code directly in their code base. And that's 10 million lines of code. This is lifetime, so it's not over the course of like a couple days. This is a course of like a year or so. Yeah, this is very crazy. Like, I think 2 years ago or a year ago, we probably could not have imagined this to be possible. Like, if I told you that someone wrote 10 million lines of code with AI, you would just feel like, that's complete BS. What are you talking about? Yeah. Also, another very cool thing, I did using Firebender, I had Firebender write SQL over our metrics database. And you can see here that like split by the top countries, Germany is the highest in Europe in terms of like people accepting code changes from the coding agent, followed by United Kingdom and Europe. And Germany is top 4 in the world for this. And so this leaderboard is cut off, but there are 100 countries on this list. US and India are obviously at the top. Ton of Android engineers in India. Yeah. And this is our internal team usage. So I use Firebender every day. We have a small team of 4 engineers right now. Everyone uses Firebender. And we essentially like build the tool with the tool. So there's kind of this weird recursive loop going on here, but it works, I promise. So yeah, that's our team usage. I think also one of the craziest things too that we're seeing as well is usually like startups and indie developers tend to adopt newer tools before enterprise. I think something like this that was really surprising to us is that like enterprise and larger companies seem to be very interested in this, and they are. I think a lot of the people that we talk to view coding agents and the ability to actually write code quickly and like high quality code as a competitive advantage, right? Like this is now something that is in their best interest to try and adopt quickly. These are some of the people that we work with. And in aggregate, they've all like accepted over 10 million lines of code easily. Some of their code bases are also in the millions of lines of code as well, with like thousands of modules. Great. So that's a primer on what Firebender is, the progress that we've made, like where it's at, and kind of like a general sense of what the coding agent can do. I think now I'm going to start like digging into the guts of it, how it works, And yeah, so let's get right into it. So again, this is chat box, how you interface with agent. Someone can type something in. We're going to go through the life of a request here. So I think one thing before I get into it is that there's a lot of, I'd say like a lot of like kind of like AI slop words that are out there that maybe a lot of you have seen. You'll hear like agent, agentic, MCP, or like RAG, I don't know, multi-agent systems or architectures, or like, I would say like a lot of these are like very much buzzwords and kind of like is not really great at explaining what coding agents actually are or how you actually interface with LLMs. And I think it's needlessly complex, so I'm gonna try and like keep things very simple and straightforward. Really it's like, it is straight up just string interpolation. Like, if you actually look at a lot of these frameworks underneath the hood, they are just concatenating a bunch of strings together. They're giving it to an LLM, and the LLM is giving a string back, and they are parsing that string into something interesting, like a tool call, right? But at the heart of it, an LLM is just a function that takes in a string and outputs a string, and that's it. And like you'll hear like these agentic systems or like MCP or whatever, and at the end of the day, all of this gets concatenated into like one big messy string. That's it. And so now you'll get to see Firebender's very big messy string. Okay, so you get a query. It says build an app that does XYZ. This query is a string. It's something that the user writes. The first step in the life of this like agent request is you'll have something like the user's current working directory, as well as like the various things about their system, like are they on Windows, are they on Mac, you know, what is the time of day right now? Like these kinds of things that the LLM doesn't have in its training data, but very relevant for the agent to actually give a reasonable response. It's very important to include in the original system prompt. So the initial prompt construction that we have here, we have a system prompt at the top that says things like, you're a senior software engineer, you're helping, like it sets up personas, like you're helping this user who is a senior software engineer, so be very concise. And then number 2 and 3 are like the things about the user system, like I just mentioned, and 4 are tools. It's pretty simple. Okay. So this is the very first tool call. In this example, Firebender makes a find usages tool. And so I mentioned here that like in the prompt originally, we had described a set of tools, tool definitions that the agent has access to. For Firebender, it's like maybe around 7 to 9 tools, depending on the situation. One of the tools is like, hey, I have an editor and I want to find all the usages of this function. Right, like I'm doing some refactor and I want to see all the files or code snippets that are using like this exact Kotlin function or class definition. In this case, it's the JetChat theme. And so it's trying to do a refactor to maybe look at the JetChat theme, see all the usages, change those files. And so it makes this tool call. And then we handle the tool call here in the IDE. And we return, again, another string that says like, hey, this is where all the Kotlin functions are that use this JetChat theme. Yeah, and so over here on the right, you can see kind of this string getting created here. At the top, again, you have the prompt construction, then you have find usages, then you have the tool result followed after that. And so you have many, many iterations. This can go on for 30 or 40 more times. Right? And like it is quite simply literally just string concatenating all the tool calls and the tool results. And it seems simple at first, and I'll talk about some of the like very messy details, but at the heart, like this is kind of the core structure of what a coding agent looks like. You'll see this in Cursor, you'll see this in Claude Code, Junie as well, and so on. Cool. I think just a quick segue that's really important. If you are creating a coding agent, something that's really important to keep in mind, as well as prompt caching. And so if you're not super familiar with prompt caching, that's OK. The way GPUs work and the way GPUs host LLMs is they have something called a KV cache. And the KV cache can only be a prefix. So you can't really, like the cache key has to be a prefix of this massive string. In this example, like you have this original prompt, right? And it's like shapes just for visualization. If any of the prefix changes in that shape, then it'll be a complete cache miss. So even if the prompt is shifted over by like a couple characters or a couple tokens, it doesn't matter. That will cause the GPU to have to rewipe all the KV cache and reload in this entire string. That's a very expensive operation. And so if you do cache correctly, then you can get like a 90% saving on all the tokens, that you use. And you also get a 2x speed up. So that is also why, if I go back to this previous diagram, like a lot of these coding agents, they purposely, even if they're including the same context over and over again, they will just do append only, where they will append a string at the end, and they won't like splice out an intermediate string, even if it's like older context. The reason why is because, let's just say I take out tool call number 1. What's going to happen is that it is going to cause an entire disruption of the cache, and I will have to repay the full cost, and the latency will double. There are different tricks around this where some people do a laddering, where they're like, OK, we'll only rewipe the cache after like maybe 10 turns. And that tends to work. But this is why a lot of the coding agents behave this way. OK. Also, to give a sense for like how expensive these things can get and like how much throughput Firebender handles each day, we process about 10 billion tokens a day. This is across thousands of Android engineers literally just spamming the coding agent over and over again. And so it's very critical for us to have the infrastructure to also cache properly. Otherwise, like if we have some regression and we do a cache miss, our cost literally 10x, like immediately. And so that gets very stressful, obviously. But yeah. OK. So that was like generally how the string gets created. I'm going to go a little bit deeper into how agent tools work and why not all agent tools are the same. And I think this is really important because we're going to talk a little bit about MCP and also like maybe some of the downsides of MCP and like what to look out for and just have a good mental model around these things. I think a lot of agent builders initially, like if you're using Coog or LangChain or whatnot, like each engineer gets this aha moment where they're like, okay, I have this LLM in a loop, which is just what an agent is. I'm going to now just give it as many tools as I can give it, right? Like we'll give it access to my Slack, my Figma. We'll have it try and do my job. I don't know. And so you get this absurd list of like 50 plus tools. And I think in reality, what the issues are here is like a lot of engineers quickly find out, as we did, is that whenever you start increasing tools, like the actual tool count that goes into an agent, you increase the decision fatigue of these LLMs. You also decrease the chance for there to be like in-context examples of the tool. So one example of that is like, our agent uses this grep search tool where it can search the code base very quickly, right? And so if it does that many times, on the subsequent tool calls, Claude 4 will see like, oh, when I did grep search, I had this input and this code result. And so that actually tells the LLM how the tool works. Like it gives like a real life example of how that tool works. And that's what actually improves its ability to continue to call tools over time as it's like trying to handle your prompt. Whenever you have something like 50 or more tools, it just can't do that for every single tool, right? It's not going to call 50 tools, and 90% of the tools, it's probably not even going to call anyways, and it's not going to be useful. And you also have a higher chance of something called like this description collisions, where inside the tools themselves, they will say like, hey, when this situation happened, you should call this tool. And another tool might have a similar situation. There's a lot of ambiguity there. And that kind of degrades the agent performance. And so, yeah, like MCP is powerful, but given this first principles thinking, it also means that you have to use these kinds of like MCP servers very wisely and also conservatively and understand like, hey, if you give it all these tools, these agents are going to start degrading. This is, okay, the slides are out of order, but that's okay. Yeah, one funny thing is that about like 8 months ago, an engineer had ordered pizza in Android Studio. I think this was the first pizza probably ordered in Android Studio ever, so that was cool. You can see here they use an MCP to do it. You can see the chat log here. I'll read it out loud. I'm hungry. Can you order Papa John's cheese pizza and Pepsi, please? And that was the prompt, and you can see the MCP calls. It actually opened a browser, so it opened a Chrome browser. It went to papajohns.com and started clicking on things and just ordered a pizza. So yeah, and there's the pizza there. That was really cool. That was posted on a subreddit, so I thought that was really funny. Enough distraction. Back to what I was talking about with the MCPs. So this is an example configuration that I've seen in the wild in Firebender. One of the engineers that we worked with, they had an MCP set up for Figma. They had one for Slack, for Jira. Makes sense. Like you would want to connect all these things, especially if all of your code data and like all the context of your work is going to be in these tools. So what they were trying to do is they were trying to just say like, hey, here's this Jira ticket, go implement this. Here's the Figma URL for the Jira ticket, go implement this. I'm going to go get coffee and not work. And that was the dream, right? And it makes sense. Like this is a very, very beautiful dream to have. But in reality, what happened is, again, like the same situation where they tried it, they committed it, and they gave it to their entire team to use, and it started hurting the performance of the coding agent. So I urge you, like one big takeaway of this talk is when you do team-wide configurations, whether it's on Firebender or Claude Code, really audit like what you're putting as a default, and if you're bloating up the tools for the coding agent, it could hurt the performance for everyone on the team. I think over time this will become less of a problem, but right now this is a very big problem that we see. So, yeah. And potentially in the future, I think a good workaround for this is doing something like subagents, where you have various configurations of the coding agent, where you have like, oh, this agent is specifically only going to do refactors. So give that agent the tool for find usages, grep, maybe a structural find and replace in IntelliJ or Android Studio. And you can have a different agent for doing specifically Figma to compose. And that seems to be like the best architecture here. And you have some like auto balancer that chooses between the agent configs. Yeah. Okay, so that was tool calls. And I also discussed the string interpolation. I think now one thing that is extremely important to mention is how to write good evals for coding agents. there are a lot of problems that come up when you have a coding agent that has thousands of engineers. Like if you make a prompt change, for example, right? How do you know that this isn't going to cause like a massive regression in production? Like if we just change the string and all of a sudden, like Firebender agent starts behaving extremely weirdly, like starts speaking maybe not in English, for example, like that is extremely concerning, right? We need to make sure that our coding agent doesn't have any kind of regressions in production, and we want to know that immediately. So we want to evaluate the agent anytime we do any kind of code change, architecture change, prompt change. These are the kinds of tests that we run beforehand. Many of you may not have heard of Kotlin Bench. It's something that's open source that we built internally, and then we're like, okay, let's give it to the rest of the community. The way Kotlin Bench works, first of all, before I go into that, we measure LLMs on various coding tasks. And here you can see GPT-5 as like the current state of the art, and then also several other of the frontier LLMs. And so this is really important because it's like, okay, well, what LLM do I pick as an Android engineer or just an engineer that is most effective on Kotlin specific code? A lot of the benchmarks that we see, like the Amy benchmark, the terminal bench, a lot of this is very general. It's like most of it is actually written in Python. So if you look at Aider benchmarks, you'll see it's all written in Python, and that's not very relevant for Kotlin and Android, and a lot of it is out of date. So it's really important to actually see how well these models do on real-world Kotlin tests and Android tests to actually test if they have the knowledge that we need. And so the way these benchmarks work is we scrape hundreds of Kotlin repos. So we scrape hundreds of Kotlin repos and then thousands of PRs on these repositories. So now we have like all the inputs, which is all these repos and PRs. And then we filter the pull requests for quality. So we make sure that each pull request has testing, like an engineer actually implemented tests in that PR. And then what we do, which I think is kind of interesting, is we undo the non-test changes, and then we freeze the test changes, but we don't tell the AI about the test changes. So like these test changes are hidden, completely hidden from the UI. Then we tell the AI, like as a coding agent, hey, here's the PR description, and here's the GitHub issue. Go ahead and implement this. You don't know anything about it besides just the ticket and the PR. I want you to now implement these things, and here's the repo. Go and do it, right? After the AI coding agent does the change, we then tell it, okay, now we have this automated infrastructure and we reapply the test changes. So when we reapply the test changes, it has this interesting effect where now we can just run these test changes in an automated way, and we can actually verify whether or not the code that the AI writes passes those test changes across thousands of pull requests. Right, and because the AI didn't know about the tests and didn't see the actual like human changes, this gives us like some general sense of like whether or not it's performing well and passes. Is cool. So we run all the tests to verify that all of them pass, and that's Kotlin Bench. Also, I think something that is kind of insane, and maybe it's because like we're a startup and we're in like this SF San Francisco bubble across the world. On our benchmarks, over the span of like 4 or 5 months, right? We started like just in March 25th, 2025, and 2.5 Pro was the state of the art then, with about 14% correct on Kotlin Bench. And in just a couple months now with GPT-5 and high reasoning, we're now at around 30%. So, yeah, it's kind of crazy. This was not, like, we did not expect this kind of progress, and it's something that we're watching closely. I think what this tells us, though, is twofold. It's that these LLMs are getting smarter very quickly. I think separately, it also means that we need to create harder and harder benchmarks. Like this benchmark might be another benchmark that's saturated, and very soon maybe we need to have an open source benchmark that test these LLMs on their ability to create full compose screens, or test their ability to create full Android applications from scratch. Because ideally, we want to see that it's like 5% passing or 10% passing, not 30%. And this is another diagram of the benchmarking process and how it works. Cool. Okay, so I explained kind of how Kotlin bench works as an example, just to give you guys like an understanding of how this looks in practice. I think this is maybe more so just a general structure for how to think about good evals. And this is also the kinds of questions that we ask internally whenever we're writing our own evaluations. So the first question that we ask is like, okay, what is the end goal state that the AI agent is supposed to get? Like, what is the output? And then is the output non-deterministic? Are there many possible solutions to this output? And can we programmatically verify? And being able to programmatically verify is extremely important, because this means that we don't need to have a human manually seeing like whether or not these tests pass and verifying. We can just run this at scale and have a pretty good benchmark. And we have many examples of this as well besides Kotlin bench. The other 2, 3, and 4 is pretty general. It's like, okay, let's say that now the end state is programmatically verifiable. Can we also create a sandbox environment where the agent can get to a verifiable state? So this means like, can we run in a cloud VM and run it on a loop and just massively parallel scale that? The other thing too as well is there a way to get sufficient data, input and output from, public training data, online repositories, maybe even our own internal training data to actually create a statistically significant result? And so we do things like statistical significant analysis, the Bayesian A/B testing to like try different models to see if they actually do create improvements or if our prompt changes actually are working. And so also reporting as well to like get good dashboards to visually quickly understand what's going on. And this is one example of many internal benchmarks that we have, but there's this really hard problem of making code edits. It seems trivial, like, okay, tell LLM to maybe rewrite the entire file, but that's really slow. How do you get an LLM to actually describe a code change is quite difficult. A lot of credit to Aider. They're an open source terminal coding agent who pioneered a lot of this work. One thing that they did here is that they created this Git unified diff where they had the LLM write a Git diff and try and apply that patch programmatically. We found internally that that did horribly on our benchmarks, partly because LLMs are not pre-trained on unified Git diffs. All you see on Stack Overflow is markdown of a code snippet, right? That's what LLMs understand in their pre-training, and so this does not work well. And instead, what we ended up doing is a form of some speculative decoding approach where we have a smaller LLM take in the code snippet and rewrite the entire file at like 2,000 tokens a second. And that turns out to work much better than applying a diff patch. And so this is an example of us showing that you should be able to investigate samples here and look at why the diff is incorrect. Okay, for the sake of time, I'm gonna skip this. If you want to read more about Firebender, there's a really good AMA on r/Android Dev about us. I go into details also of how we went about building the startup with 3 people to getting enterprise contracts with a lot of big companies like Zillow, Instacart, and OpenAI and Square. And so I recommend reading that. It's a good case study on just startups, business, if you're curious. The 3 of us lived in a 2-bedroom apartment for a year. My younger brother was living in the hallway, so that it was very sweaty. We were working a lot, and also just working in our living room. That was our office. So I highly recommend reading it. I think it's interesting. Cool. And this is our engineering blog as well. We write a lot about our coding agents and all the problems that we see in the field. It's a good read. I think it's interesting. So it's there, firebender.com/blog. Yeah. Thank you. Yeah. Thanks for coming to this talk.